Have you ever wanted your computer to communicate with you in natural language? Or use common sense reasoning in your applications? Or explain its reasons, and have reasons to explain? Or learn on its own, and manage its own learning? Or learn and use its own rules that make sense to you? If this describes you, then you have found the right presentation. Our goals were to find and demonstrate ways that utilize Psych's unique features, showing that it is able to help expand its knowledge, and that the knowledge it possesses and collects is a form of common sense that can be applied to various applications. Several projects were started to progress towards these goals. CynD explored the use of Psych's knowledge in the environment of a video game, both as an aid towards natural language processing and for environment generation. BURC explored using statistical natural language processing over large bodies of text to extract common sense assertions for inclusion into Psych. Weka and Psych demonstrated giving Psych access to open source machine learning tools to generate new rules and recognition processes for itself. And Cyclopedia covers work on linking Psych's knowledge to the Wikipedia. In the CynD or CynD system, several things were demonstrated. At the start of the Psych project in the mid-80s, desktop computer games were fairly simple and character-oriented. During the 90s, computer power and software optimization made possible 3D graphics to steadily improving realism. Current desktop games include such features as physics simulations, atmospheric effects, and ways of specifying character, behavior, and responses. Our question was, what would a system like Winograd's classic desktop agent look like using such modern technology? CynD, or Psych plus Program In plus Doom, is a system Daxtron Labs developed to experiment with Psych in a modern game environment. It consists of the Doom 3 game engine, Psych and its supporting interfaces, and our developed additions consisting of a Java virtual machine embedded within Doom and hosting a number of applications and utilities inside that Java environment. This approach was chosen, seeing that Psych's Java API is the most mature. Our initial work focused on bringing a version of our chatbot interpreter CynD to Doom characters. CynD is an AI markup language, or AIML, interpreter that can interface with Psych. AIML is a very popular language with chatbot developers because of its simplicity. Our goal was to allow conversational agents developed in AIML to access Psych's knowledge base. AIML focuses on pattern matching rules which are organized into groups called categories. This category specifies how to respond to the question, do you like something? It generates the response that it does not because it thinks that it is dangerous. Our addition was the ability to only generate that response if Psych classifies that something as a dangerous thing. This simple addition covers over 2,000 possible patterns and saves the chatbot designer from having to think of and write each. It also lets the designer focus on responses to semantic classes instead of just words. This is a simple example of using the previous category. When asked, do you like Ebola? The system responds, I do not play with Ebola because I think it is dangerous. You can use Psych to help recognize patterns and also to generate replies. Here we have a category that handles all questions of the form, who is the attribute of something? This could be, who is the President of Sweden, or who is the mother of John. Here are some examples using that category. Note that the version of psych used did recognize spouse, but did not recognize wife. In the first case, it answered directly. In the second case, it gave a standard chatbot response. But some things are best shown in motion. The viewpoint is from the player's perspective. The room layout and characters are generated from a psych microtheory. The psychbot will query the knowledge base for the user's current location and plot a course there. One condition is that the psychbot can see the player in the KB. So the player is moved so that the bot can see the player from down the hall. The psychbot at the far end of the hall can now see the user. Information on the bot's sensing and environment are mirrored in the KB. All bot responses are based on checking the psych KB for answers. While the bot makes the long trek from the far room, several questions that demonstrate the prior question answering methods discussed previously are asked. The responses are generated from knowledge already in the psych KB. The processing of questions are queued, and the bot may respond to questions prior to the last one asked. Sometimes you want to know that the bot is still thinking. The PsychBot is finally at the room where the player is located. The key feature of CynD was integrating Psych at multiple levels of an existing complex system, including reflecting character conditions in the KB for generating character responses, and generating elements of the environment based on separate elements of the Psych KB, something that Psych's micro-theory and context systems allow. PsychOr's founder, Douglas Winnatt, has stated an hypothesis that once Psych reaches a certain level, it can help in its own development and knowledge expansion process. Dijkstrom Laboratories has done work. The other major theme in our work has been using Psych's existing knowledge to expand Psych's future knowledge in various ways. These include learning common sense associations via reading, learning rules via induction, using Psych's existing knowledge to organize various machine learning tasks, and linking existing concepts in the Psych KB with Wikipedia articles for future knowledge extraction. BURC, or Bootstrapping with Research Psych, was our first learning-focused project. Its goal was simple: read text and extract common sense associations from it. These are some of the things that BURC demonstrated. The basic inspiration for BURC was a shotgun approach to genomic mapping, which breaks the genome apart and looks at millions of fragments, and finds overlapping commonalities to reconstruct a complete model. Our question was, would a similar approach work for common sense extraction? BURC processes the text of the British National Corpus Database, using the output of the CMU link grammar parser distributed across a small cluster of computers. The fragments are then merged and placed in a database, and then analyzed using Psych's existing knowledge to generate new hypotheses that are in a format that can be included back into the Psych KB. The key element is the system is looking for fragments of associations from detailed parsing. As such, the parsing takes longer than shallower methods. But luckily, parallel processing methods can also be used to make the task manageable. Mining was done over the most frequent adjective-object associations and subject-verb associations. In each case, this selection resulted in picking the most frequent 15% of fragments for each class. This resulted in a large reduction in the amount of information processed in later stages. The BURC process generates a similar number of assertions for each constant as had been generated manually. It remains to be processed over large bodies of text like the Internet, and of course the quality of the assertion needs to be verified. However, the task shifts from generation of common sense, a typically hard task, to verification of common sense, a fairly easy task. BURC showed that Psych can help in its own knowledge entry, and that it contains enough knowledge to filter out bad associations. These are some of the things that combining Weka and Psych demonstrated. The goal of combining Weka with Psych is to provide Psych with a set of open-source machine learning tools. We use Weka's machine learning toolset because it is written in Java and thus can utilize the matured Java API for Psych. It provides multiple classifier types including decision trees, support vector machines, neural networks, and others. and it enjoys an active developer and user community, resulting in constant updating of methods. Weka also has a number of parallel computer-based versions, which aids in future scalability. A daemon process queries Cyc for learning tasks and extracts the parameters and performs them using Weka. This allows Cyc's inference rule to generate new tasks and their parameters. The information on the instances used for induction can be stored in Cyc, and again Cyc's knowledge can be used to fill in any missing information. The daemon process then runs the requested learning algorithm and either inserts the discovered rules in Cyc or places the required hooks in Cyc to use an external Weka classifier. The first test of the system was in the area of spam classification, using only the subject line of a message. This is a task that humans use common sense knowledge to recognize non-solicited email. Given a representation of an email message, Cyc's knowledge is used to add all the semantic classes known for words in the subject line. The machine learning engine then uses the semantically enriched representation to generate spam classification rules based on the semantic class of the words. Given a sentence like, "amazing home loans at low rates," the semantic classes of each word is looked up. This produces a very large list. Weka's task is to find the common pattern when this is done for each email message, and what separates spam from non-spam. Bit by bit, it builds a tree based on those semantic features that distinguishes regular mail from unsolicited mail. And by decoding the tree, it can generate rules for Cyc. This is an example of a rule generated. If something is a mail message, and it does not mention being free monetary cost or making something available, but it does mention a legal agreement, then the message is spam. This is an example of the type of lines that it catches. Note that the rule is specified as a bag of concepts instead of as a bag of words. WAC showed that Cyc's knowledge can help machine learning tools operate on the semantic level, and that when added to Cyc's sea of assertion, the rule generated could utilize all of Cyc's existing knowledge. Future work on Weka and Cyc involves getting Cyc to notice learning opportunities, which will be an important area to study. Cyc has the ability to interface to external data sources, and learning new rules can tap that information and let the system learn new uses for existing sources. As the system learns new rules, it can utilize the output of those rules as input conditions to learning new rules, and expanding the system to access the full set of tools provided by the Weka toolset. And finally, some things demonstrated by the Wikipedia linking project. This work is being done in support of the Cyc Foundation. The goal of the Wikipedia linking project is first to identify the relationship between existing Cyc constants and Wikipedia articles, linking browsing of both resources as a prelude to future, deeper knowledge extraction projects. We've been working on both manual linking and automatic linking by using 9,000 mappings done by the volunteer researcher Sudarshan Palil. Sometimes linking is easy when the Cyc name and the article name are close, but other times the article can denote a slightly different concept or refer to a metaphorical use of a term for, say, a product name. Can we learn to distinguish Ford Mustang article from the Horse Mustang article without deep parsing? We believe so, if you can utilize Psych's existing knowledge to organize those articles that have already been mapped, allowing it to bootstrap the mapping of remaining articles. For various Psych class concepts, we can automatically create article recognizers for that class utilizing existing statistical natural language processing techniques. The method and accuracy is similar to that for statistical spam classification. If used in the future for selecting learning articles from the web, the ability to reject noise articles will be very important. This system is in the earliest stages of development. We start with a local Wikipedia article that has been mapped. We ask for the Psych view, which is a special page type that we created. The Psych view page shows that the article has been mapped, and Psych knows some facets about Mr. Reagan, and that there is a Psych constant to represent the article. In Psych, we can see what the article is about. That is, in this case, Mr. Reagan. We can go back to the article to check one of its facets and see what Psych knows about that term. Once back at the Psych view page, we can see that it contains the entire text of the article. The page also has provisions for manually associating the article with plausible Psych constants. In conclusion, we have found Research Psych useful in each of the areas explored, and Daxtron Lab looks forward to continuing research and development in each of the areas indicated. Information on some of the topics discussed can be found at the following websites. Thank you for viewing the presentation. If you have any questions, comments, or suggestions, we would like to hear from you. Please contact us at rpsych@daxtron.com. I hope that you found the topic interesting and stimulated your own thoughts about how you would use Psych.